So I will now share the slides. Okay, here we go. This is the first chapter of today's lecture. We'll first talk about mechanical properties. Let me first just give you a list of the basic groups of functional properties. So we start with mechanical properties. We're going to talk in details about this. Then there are thermal properties, properties about the thermal behavior of the materials. Then we have electrical properties. This will be the topic of tomorrow lectures. We have optical properties. We'll cover this today. Then there are magnetic properties. This will be given, if I'm not wrong, on Friday during tutorials. And some other properties which we're not going to discuss during this course, and these are acoustic properties and radiological properties. All these main groups of properties, they have their own subgroups and a variety of different properties within this basic description. So now I give you an example of electrical properties. You know, you got a number of different properties within this group. And of course, we're gonna cover a majority of this really, but this is just for you to understand that when we are going into discussing one group, we are discussing again a variety of different properties within this group. For instance, optical properties, again, you see a lot of different properties, how light interacts with the matter. But now, okay, as I said, we're gonna do mechanical properties. Now, when we talk about the mechanical properties, we have one standard test for the mechanical properties of materials on the basis of which we can define their particular properties. And it's called a tensile test. A tensile test, I will describe it. So what you see here is a kind of, you know, like a sample that we have to prepare for this tensile stress. And we clamp this sample with the ends, these white ends, into the instrument, which is capable of apply the tensile stress on this particular sample. Now, really, it is tearing it apart. Mostly we call this instrument Instron because it's the major producer of the instrument. So what we do with the instrument, we pull this sample apart and measure the force that we use for this pulling. And we also measure the deformation during the pulling. So this is the, you know, like a very known strain stress diagram. Now, first of all, I would like here to define what strain and stress is. You know, I'm a professor, I can mix it up, but you're students, you're not allowed yet. So I'm joking, but people really kind of confuse strain and stress a lot. So strain is deformation. And we define relative strain as the deformation over the initial dimension. Now it can be linear, as it's shown here, linear because for this particular test, the linear change in the dimension is relevant. However, stress is the force per cross section. And basically, we're measuring the force and the deformation during the tensile stress. So now we're gonna go through this particular stress strain diagram. So as I said, we clamp this kind of sample into the instrument and then start pulling it apart. Initially, the deformation, the strain, will linearly depend on the applied stress. We call this part of of the deformation elastic deformation, because it is elastic in the term, then when we remove the stress, the dimensions of the sample, they go down to the original length. So this stress is reversible. The strain is reversible. The strain is reversible. However, when we overcome this particular point here, which we call yield strength, the plastic deformation happens. The slope of this elastic deformation, the slope of this first part, is called the Young modulus. We will define this later in more details. So, as I said, here then we start with the plastic deformation. If we now remove the stress, the sample will not go back to its original shape, but it will permanently be deformed. So we come to this upper point here. So I can also illustrate this with this little cartoon here. You see, this is now elastic strain, nothing. Well, up to this point, we can return the sample back to its original shape. And then at this particular point, this is the plastic information. At this particular point, something happens. Actually, what happens is that the plastic deformation starts to reduce the cross section here in the middle. So we call that necking. And because the cross section now is smaller, you see the calculated stress is higher, or what we can say, we need less force. We need less force to further plastically deform the sample. And eventually we will come to the fracture point when, of course, the sample will fracture. Now, next, I would like to go a little bit more in details about the elastic deformation, plastic deformation, why these two deformations are so different, and what is atomic reason for their deformation. So we already said that this is the elastic deformation is linearly proportionate to tensile strain. And it's very important, it is reversible and instantaneous. So there's no time delay. It happens when we apply stress, it happens immediately. The proportionate coefficient of proportionate is called Young modulus. And actually this is just the slope of this particular relationship. Now we can go back to what we have seen yesterday, the potential well and the strength of interatomic bonds. We can easily understand that if these bonds, if the strength is high, if the potential well is deep, then the Young modulus will be high. The slope will be high and the sample will be not very much elastic. So if the strength of the bonds is not so high, if it's low, if it's weak, then this curve, this linear part will be, the slope will be low, will be small, and the material will be highly elastic. About plastic deformation. So we said that the plastic deformation starts at the point which we call the yield strength. After the stress is removed, we don't get the original shape of the sample anymore, but the sample remains permanently deformed. Now, we also said that here at the highest possible tensile strength, the necking occurs and we get the reduction of the cross section of the sample. And that then comes down to fracture strength, where of course, the catastrophic fracture happens and the sample is destroyed. Now, we will try to understand what really inside the crystal lattice is responsible for the plastic deformation and for the yield strength, how that correlates to the crystal structure. So we will kind of try to microscopically describe the plastic deformation. Now, one first picture that we can imagine is that, of course, in let's say, metal, in the structure with the atoms of the same kind, we have these layers, different layers of atoms. And if we kind of pull them apart, they can slip one over another, as it's shown here. So we apply some kind of shear force on these layers, and they just slip and move, like it is shown here, for one atom line over the bottom layer. So this picture seems reasonable, and of course, based on this very simple picture, we can calculate theoretical yield strength for different materials. We know that if we do this slip, then one layer must kind of move for some particular distance up in order to be able to overcome the atom on the bottom layer. And from that, we can calculate what kind of force is required to do that. So here are a few numbers. For steel, that would be 7 gigapascals, and for copper, 4 gigapascals. Now, but the problem is that if we experimentally measure these values, they are like significantly lower, for orders of magnitude lower. So that means that this theoretical model does not describe properly the plastic deformation. This is certainly not the proper description of the plastic deformation. So we need to find something else. And this is now the time when we are moving towards the defects in the structure. So really, the whole deformation process is divided to little steps, which are facilitated by the presence of dislocations. So actually what we cause with the applied force, we cause the movement of dislocations. Of course, that in fact this is movement of the atoms, or let's say so, it is basically a break of some atom bonds and creation of other atom bonds, as it is now shown in this picture. Now, if you count atoms here, bonded atoms here, you will count them 5. But then what happened is that this particular bond, which is near to this location, broke, and the new, the new bond was created between these two lines. So, and now here we have only 4 atoms here bonded, and then is dislocation coming. And this then continues further on until the dislocation reaches the surface of the crystal. And because this slip now is divided to small steps facilitated by the dislocation, we need much lower yield strength. So now you would say, okay, the dislocations, they cause the material to be less strong, which is correct. However, there is turning point somewhere. Namely, if we introduce some very high number of dislocations into the material, then dislocations themselves, because they're not necessarily all in the same orientation, they start to pin each other, and they would prevent their movement as we have described it here. And from that dislocation concentration on, the material will start to become more and more strong. So here is the case of such a material. All these little black lines are dislocations. And as you see, there's many of them and in different directions. And this is the case when they start to pin each other and they toughen the material. And this is what we call forging. Forging is a method to introduce more and more dislocations into the system, so many that we will end up, instead of with weaker material, we will end up with much, much stronger material. Now, forging is quite historical thing. Of course, the blacksmiths in the past, they didn't know that. But empirically, with the experience, they have come to the knowledge, to the wisdom, that if more they hammer the steel, the iron, more they hammer it, stronger it becomes. And now I would like to, well, remind you to the Japanese history. You know, Japanese swords and the masters, blacksmith masters that they were producing swords were very appreciated, especially the best ones. And now we can ask ourselves why some were better and some were not so good, and why some swords were appreciated more. Well, it's very simple, because the appreciated, the good blacksmiths, they were just working harder. So they were hammering their steel harder, and they were hammering steel, fold it back, hammering again, fold it back, hammering again, until they have introduced a really dense concentration of these dislocations into the steel. And when they have finally produced the swords, these swords were much stronger than the swords of some other more lazy blacksmiths. It's just about hard work and sweat. Okay, let's also go through some other mechanical properties, like brittleness. Well, you see, all these properties, just combination of the basic properties that we talk about like elastic and plastic deformation. So brittle material has got very little elastic deformation, or almost nothing really. You know, this slope is very steep and doesn't extend far. The strain is minimum. So the brittle material can in fact absorb relatively little energy before it fractures. It also hasn't got much of plastic deformation. Immediately when it starts, it is a fracture point. The other type is ductile material. Ductile material can be deformed plastically very much. So they can really absorb a lot of energy before they fracture. You see, the amount of energy they can absorb is equal to the surface below the curve, the tensile curve. So you can easily see that there is a lot of energy present in the ductile materials before the fracture, while much less in a brittle material. The brittle material also, they fracture without any plastic deformation, while that is its opposite for the ductile material. Then we talk about toughness. Toughness of the material is the ability of material to absorb a lot of energy without fracturing. So not necessarily all within the plastic deformation range. So this is the difference between the ductility. Ductility its ability to withstand a lot of plastic deformation, while toughness is the ability to withstand, to absorb a lot of energy. So tough materials are not necessarily ductile. So we talked about elasticity, so the bonds in elastic materials are not so strong, are weaker, and that allows for a lot of elastic deformation before the plastic deformation happens or before the fracture happens. And then we got one interesting property of material, and that is creep. Creep. So, you know, we apply some stress on material, but nothing happens immediately. But it happens slowly. The material slowly deform under this applied stress. That can also be on the time scale of days, weeks, or even years. So creep happens, as I said, very slowly, but it is a permanent deformation under the influence of some permanent mechanical stress, persistent mechanical stress. So, and then we come, to hardness. The hardness is something local, not like we have been talking before. We cannot describe with a tensile stress curve. It's a local, and it's ability of material to withstand local plastic deformation, abrasion, indentation, or wear. So when we talk about hardness, we have this kind of empirical Mohs hardness scale, where we put diamond on the top with a number 10 and talc at the bottom with the number 1. And then we define these units based on the hardness of particular reference materials. Well, I already mentioned that diamond has got 2 polytypes, and the one with hexagonal structure is tougher than a cubic diamond. At that time, when this hardness scale was constructed, this knowledge was not present yet, so it does not appreciate this fact. But anyway, it is good to empirically describe the hardness of different materials. In general, we can test the hardness of materials. So the material with high number should abrase or scratch the material with low number. So diamond would scratch corundum, and corundum would scratch topaz, but not other way around. So few of technical materials. So one of the strongest technical material are nitrided steels, which comes with a hardness of almost to the value of 9, very hard material. Cutting tools are between 7 and 8, and then you see there's regular steels, not special steels, are between 4 and 5. Plastic is down to basically 1, somewhere near to talc, maybe a little bit harder. Okay, now with this, I would like to start with mechanical properties, and maybe I can invite you, if you have some question regarding mechanical properties that we discussed them now. So I'm going to stop sharing for a while and wait if you have some question regarding the mechanical properties, and then we will continue with thermal properties.
Any issue?
Is there any question regarding mechanical properties?
Yes, sir. We have one question. I'm just pasting it.
Okay. Okay, I read the question for everyone. Graphene is said 200 times stronger than steel. How it is measured? Since the graphene sheet is very small, is it possible to test mechanical properties in micro and nanomaterials? Well, yes. Now we have to understand a few things. Graphene is two-dimensional structure. Yeah. So it's really measurement is performed on with a well, first of all, all these things when it comes to graphene, because of such a regular structure and periodic structure, this can be easily calculated. Most probably all these numbers have been obtained by ab initio calculations. In addition, I would now talk about graphene, nanowires of carbon nanowires, for instance. They are very strong, even stronger than graphene. And nanowires are strong in one direction, in their main direction in which they grow. And of course, they're very strong because they're all just very strong covalent bonds connecting the atoms in the nanowires. And then, because nanowires can be grown to some kind of mesoscopic scale, really, they were really measured by same approach, just of course adjusted instrumentation, but the same approach. They were just pulled, and the force were measured how they were pulled.
Thank you, Professor. Participants, if you have any question related to the this mechanical properties, you can raise your hand. Because today, sir is able to hear us very clear. You can interact directly with the professor.
Okay, nothing?
No, sir,
Sure.
nothing.
Shall we continue?
Yes, sir. Yes, sir.
Okay. Okay, I will tell you. First of all, I will explain this picture to you. This is a man holding a glowing piece of material in his hand without getting burned. Is that possible? Well, yeah, obviously it's possible. I hope you will understand this at the end of this chapter. And then I would like to tell you some story from the past. Now, the space shuttle mission. Space shuttle mission was delayed for many years. And the reason was that they could not find a material that would properly thermally insulate the space shuttlecraft during its return into the atmosphere from the space. So it was a big international effort to find this kind of material that can be put on the shield of the craft and thermally isolated. So after many years of investigation, the institute in Germany has developed some material based on silica. And this is this particular material which this person holds in his hands. This material is characterized by very low thermal conductivity. So even if it's hot inside, this heat does not come on the outer surface, and therefore this outer surface is still cold enough. So we have now, today, we have another big challenge when it comes to thermal properties. Fusion. To fuse together in like a fusion reactor, as we build it in France, in ITER reactor, for instance, to fuse together deuterium and tritium, we need about 1 gigakelvin temperature. Well, it is pretty much possible that to do that on the sun, where actually this is happening. Well, here we don't have a vessel, we don't have a material where we can do this, because you can imagine every material would just melt, burn, be destroyed at that temperature. So for this reason, we have to run the fusion. We have to capture the deuterium and tritium atom in the space by magnetic field in order to prevent their contact with the walls of the fusion reactor. And this is the biggest challenge of today. The challenge, if properly resolved, can really save our planet from all this carbon dioxide emission, pollution, greenhouse gases emission, and global warming. That would be perfect, clean, and cheap energy. Okay, let's now go into the specific properties that define the thermal behavior of materials. So we start with heat capacity. So heat capacity is amount of heat energy that a material can absorb, that 1 mole of material can absorb to increase its temperature for 1 Kelvin. We also can define a specific heat capacity, and that would be the amount of energy that 1 kilogram of material can absorb to increase its temperature for 1 Kelvin. So again, the heat capacity here is just constant, proportionate constant between the change of the energy and change of temperature. But did you ask yourself what actually happens in material? Why one material is warm and another is not warm? Energy is something we can't touch. Really, energy has got no material platform. So what actually happens in the material when it heats up? So what happens is that a vibration of particular atoms or ions actually changes. It becomes more intensive. And this is what we feel as a heat of material. And this is what actually increases temperature of the material. So we can say that material accumulates heat by increasing its vibrational energy of atoms. So we must know that atoms in every solid, they vibrate all the time. They oscillate in many different ways. But these ways are not chaotic, hectic or so, but they are coupled, organized in ways of particular modes. And these waves, they can couple together and they propagate through the material. So they formed so-called vibrational modes. And these vibrational modes can be of different frequencies. So with higher energy, we wake up high energy modes, for instance. And they're also not of any kind of energy, but they are with a defined energy. Every one mode has got defined energy. So we say that vibrational energy is quantized, like it is electromagnetic energy, as we know. And when we talk about a quantum of electromagnetic energy, we talk about photon. And when we talk about a quantum of vibrational energy, we talk about a phonon. Now, another important property of the heat capacity is that it's not temperature independent, but it's temperature dependent. Well, heat capacity towards 0 Kelvin is 0 for all materials. But then it starts to increase. We are waking up new vibrational modes. Now, we can also define here something called Debye temperature. And we define it as as the highest temperature that can be achieved due to a single vibrational mode. So only one, if we would have only one vibrational mode, with this particular mode, we can reach up to the Debye temperature. Now, for majority of, for a lot of materials, I wouldn't have majority, but a lot of materials, the Debye temperature is just like slightly below room temperature, or yeah, we can say like that. So the room temperature is somewhere here when this curve flattens down. And for that reason, a lot of material has got a heat capacity pretty much similar. It's about 25 joule per mole per Kelvin. Or maybe yeah. Some of them, they got the Debye temperature at higher value, so their heat capacity at room temperature therefore would be somewhat lower. So like we have here silicon, as I show it here. The Debye temperature is, as you see here, over 600 kelvins, and then the heat capacity falls down below 20 joule per mole per Kelvin. Some very significant exceptions are also beryllium. You see, heat capacity is even lower than for the silicon. And carbon. Carbon is always something special. Here, the heat capacity is even lower. But from the other side, there are also materials or substances with higher heat capacitance, and one of them with the highest heat capacity is water. You see, liquid water has got heat capacity of 75 joule per mole per Kelvin, and this is again because of the hydrogen bonds that we have discussed yesterday. They allow into the water for many modes of vibration of these water clusters, which can actually absorb the heat. Now, ice is already more restrained with its movement, and therefore the heat capacity of ice is much lower than of the water. Fine. Now we can talk about the thermal expansion. You know, when they start building railways, they were not aware of the thermal expansion to be such a problem. So they build the railways, kilometers and kilometers of railways, and then some cold day came and they cracked, or the heat made them, you know, deformed completely, because the steel, as any other material, because it expands with the temperature. So we can here define the linear expansion coefficient for the material, which is again just a coefficient between the relative deformation or relative extension of a material at some temperature change. Now, what is the microscopic reason for thermal expansion? So the reason for thermal expansion is in the fact that the potential well is not symmetric. So it's asymmetric. So now you can imagine an atom sitting here on this particular distance between the other atom. And we said that the atoms are thermally vibrating, oscillating. So it's, let's say it's oscillating with some particular energy, with energy A2. So you see that its average position will move slightly when the atom will oscillate with energy A2. It will move slightly towards the higher distance compared to its equilibrium distance. And if this energy will be even higher, so it means higher temperature, then this shift in the position towards a higher distance will be even bigger. So more the curve is asymmetric, higher is the linear expansion coefficient. So if, for instance, if the curve, as it's shown here, would be completely symmetric, there would be no change in the distance between atoms, and such system would have no thermal expansion. So you see again, there's an important material property which depends on what kind of bonds do we have, what kind of potential do we have in the crystal, and what kind of atoms compose this crystal. But of course, we don't always have the material, one particular body. We don't always have it homogeneously heated up, or let's say, in many cases, a material is exposed to inhomogeneous temperature, to some temperature gradient. So in that case, a part of this body will expand more than the other part. So, and this can go to such an extent that there could be fractures in the materials, and the material undergoes so-called thermal stress, which can basically cause the fracture. In ductile materials, these can be easily relaxed with plastic deformations. So, but in the brittle materials, as we said, the brittle materials don't withstand a lot of stress. So in the brittle materials, this stress causes a structural failure. Such case is like regular glass. Maybe you have experience if you pour a cold drink into the warm glass, it can crack. For very similar reason, the joints are very sensitive to thermal stress. Namely, if we have a joint of the material with a different thermal expansion coefficient, this causes the stress on the joint, and we can induce the cracks within the joint. So for that reason, it is important to combine when we weld together or connect together materials, join together materials, two different materials. It is important that we are aware of that, and that we are using only the materials with similar thermal expansion coefficients. For instance, I have listed here several materials, technical materials, with their expansion coefficients. And we see they can be very different. We can take, for instance, quartz. We know that the quartz is thermally very resistant, that even thermal shocks cannot crack it. And the reason is because the thermal expansion coefficient is so low. You see only 0.4, 10 to minus 6 per Kelvin. While other glasses, like a Pyrex glass, is the thermal expansion coefficient is much higher. We have also some metals with even higher expansion, and polymers which are can really expand very high, very strongly, very intensively. So from this we can easily see that we can combine Pyrex and Covar, but we cannot combine Pyrex and, let's say, aluminum. If we would do that, on this joint, we will easily get cracks generated by some thermal shock, while Pyrex and Covar joint will be much more resistant to the thermal shock. Okay, now I will now discuss the last group of, or the last property within the group of the thermal conductivity. And that is in the group of thermal properties, and that is thermal conductivity. So this is thermal conductivity described how fast the heat is conducted through the material. So we are talking about the transport of heat from the region with higher to the region with lower temperature. So again, we define the coefficient K, which we call thermal conductivity, watts per meter per Kelvin. And this coefficient connects two quantities. One is heat flow, and another is the temperature gradient, so the change in temperature over some particular distance. So higher the thermal conductivity, easier or faster the heat will conduct through a material. Now, how? Again, we have to ask ourselves how microscopically the heat conducts it through the material. And there are two mechanisms. One, we already talked, are phonons. The phonons can conduct their energy from one side of the material to the other side by, of course, a vibration of its modes. And another contribution is by the contribution of free electrons. Also, free electrons contribute towards the thermal conductivity. So we have to consider that together. So they all migrate towards the colder side. Why free electrons? It's just because, they at the higher side they have a high energy, and of course these high energy electrons they want to kind of homogenize their energy over the material. So they migrate towards the colder side. At the colder side, of course, they can also transfer the energy to the phonons, and therefore we would feel this increase in the heat on the colder side, heating up of the colder side. So for that reason, all the metals has got very high thermal conductivity, because they have, in the metals, we have strong contribution of free electrons because there's a lot of free electrons available there. Ceramics, on the other side, they have very little free electrons, and then normally the thermal conductivities of ceramics would be low. So the metals would be used when we need high thermal conductivity. The ceramics normally is used when we do not need, or we really want to isolate a material for some thermal environment, some hot environment, or even cold environment. In addition, the polymers have got no free electrons really, apart from some exemption. But they also have very low thermal conductivity. And there's another material, if we call it so, with even lower thermal conductivity, and this is air. And the air is important because its thermal conductivity is very low. But of course, we cannot really thermally isolate our house with air, yeah, because we cannot keep the layer of air permanently around our house, and the wind will blow it away and bring new cold or warm air nearby. But what we can do is we can trap air bubbles into different other materials, and that can be polymers or ceramics. Now, if we trap air into the polymer, we will get all kinds of very efficient thermal insulation materials, like polystyrene, for instance. And that is very good to thermally insulate our houses, for instance, where no like extremely high temperature are in the environment. However, for high temperature insulation, it is then more appropriate if we can produce ceramic foams, where within ceramics there would be a lot of air trapped, and that would actually result in a high temperature thermal insulation materials. We use these materials, to insulate furnaces or blast furnaces in the steel industry and so on, while polymer insulation materials are used for our room temperature insulation mainly. Okay, now we will have a break for half an hour, and we will start the next session in a half an hour. We will start it. And we can start it with the question regarding the thermal properties. So prepare questions till the time. I will try to answer as best I can. And after that, we will continue with optical properties. So bye till now.
Thank you. Thank you.
Thank you, Professor. So participants, as Professor Valenth has mentioned, that we'll be having half an hour break. So you can prepare your questions till then and can ask in the, another session at which will be starting from 3 p.m. Thank you.
Okay, I guess we are back.
Yes, sir. Shall we
Yeah,
start?
so if there are any questions regarding the previous topic, just write it down, type it in the chat box.
Okay, sir. That I have informed the participants. Maybe they can ask at the end of this lecture.
Okay, fine. So we're gonna then continue with the optical properties. So first I'm showing you here is the spectrum of electromagnetic uh, radiation. As you can see, it is really wide frequency range that electromagnetic energy can possess. From if we are talking now in the, let's say, in the frequency range from 10 to 4 to 10 to 22. So we are starting at the higher energies with gamma rays, X rays, and then we are coming close to the visible light with ultraviolet light, and then you see it's a very short frequency range for the visible light. We can extend it here, of course, but in general, it's very small part of electromagnetic spectrum. And you know, in the terms of wavelength, it goes to from 400 nanometers to about 700 nanometers from violet to red. Then at the lower frequency, in the lower frequency range, yes, we have infrared, microwaves, and then radio and TV waves. So mainly we are concerned, of course, about the visible spectrum range, not only in technology, of course, not only we are not only concerned about this range, you know, we use majority of the electromagnetic spectrum for some kind of technological devices. But today we will mainly talk about the visible range and how the visible light interacts with the matter. So what happens when the light meets material? Three general things can happen. So it can go through what we call transmittance, it can be absorbed, or it can be reflected, reflectance. So and altogether, this should really sum up to the incident and to the energy of the incident beam. So the intensity that is transmitted, the intensity that is absorbed, and intensity that is reflected must be the same as the intensity of incident beam. With respect to the share of these particular terms, the materials can be transparent, so majority of light is transmitted, or they can be translucent. When light passes through the material, but some absorption or scattering within the material occurs, so not all light is transmitted. They can also be opaque when the majority of light is absorbed or scattered and almost nothing is transmitted. So how the material absorbs light? What actually happens in the material? You see, for all these particular properties, we are searching for some kind of microscopic or fundamental physical reasons in the material. Now, electron absorbs the photon energy in the way that this photon energy is actually used up by exciting the electron, so by lifting the electron from one energy level to some upper energy level, actually to give the electron some extra energy. Now we know that electrons cannot have any kind of energy, that they sit on some electronic levels, on some states. So the energy that is absorbed by the electron can only be as large as the energy between the lower and the upper electrons level. So the electrons can only absorb a discrete amount of energy. So and this amount of energy can be, of course, also described in the terms of the wavelength by this equation, which is written here. Now, okay, that is absorption of light. But what happens then next? Would this electron just sit there on the high energy level, or something happens with it? Actually, after a very short time, normally after a very short time, but these times can also be quite long, this electron relaxes back to the ground state, and during this process, some photon is emitted. And this is basics for all the optical properties. So, and we can also, through that mechanism, understand that these electronic states, their structure, electronic structure, will define the optical properties. Now let's have a look how metals absorb light. So what we know about metals now are that in their energy bands, that there is a high density of particular energy levels. So high that we normally describe as these bands as continuously populated. So when any kind of energy would meet the material, any kind of light, with any energy of the photon, would meet the material, would interact with the material, it can be absorbed because it's always available high energy level with the same energy. So all photons, regardless their wavelength, regardless their energy, will be absorbed in an upper layer of a metal. And that is just like maybe 100 nanometers of the metal. And of course, for that reason, no metal is transparent. But that, what happens later? Later, again, this electron can relax, and not necessarily to the initial state, but to any state, and then any kind of photons again will be emitted. So because the photons will have all kinds of wavelength, we will see them as white light. In fact, what we see is this silver shine of the metals. And of course, this is what, as we also sometimes call reflection. So it's just this emission of everything and relaxation of everything in the upper layers of a material. So the part of the reflected light is high. It's almost all light is reflected, just a little bit is lost. So we are coming up to 90–95%. But you may ask now yourself why the gold is then yellow, or copper is like, reddish. Now that can all be explained with the inhomogeneous population of energy levels within the energy band. Some parts can have higher density of states, and there will be more absorption in that part of the band, while other can have low density of states. And so when this population of levels is pretty much homogeneous, we will get a silver shine. but like in gold, in carbon, it's not so homogeneous. So we have preferentially or the photon that are emitted from with the energy that corresponds to yellow and red are more, and therefore the shine is a little bit colored. Now we have to talk about absorption of non-metals. The mechanism is different, so I talk about these two groups of materials separately. As we know, non-metals then have a band gap, and the optical properties are therefore significantly different. Now, a non-metal with a band gap cannot absorb all the phonons. It cannot absorb the phonons which energy is lower than the energy of the band gap. Because in that case, it should come up to some intermediate state which is forbidden, which is not there. So it just cannot go there. So the non-metals can absorb only photons which energy is higher, equal or higher than the energy of the band gap. So we can describe this with this expression here. So what happens next? Or let's first say so, we have defined already the limits, the wavelength limits for the visible light from 400 nanometer to 700 nanometers. So from that and this expression here, we can easily calculate which band gaps will be able to absorb the visible light. So we can see that the non-metals with band gap which is above 3.11 electron volts cannot absorb visible light. On the other way, the band gaps with the non-metals with a band gap of 1.8 electron volt will absorb any kind of visible light. So both will not have color. It will be either transparent. It will be transparent. While if the band gap is between these two numbers, we can get colors out of the material, and I'll explain why. Now let's say we have this material which absorbs the high energy photon. So this photon can go to the bottom level of the conduction band, but if it has got much more energy, it can go even on some higher levels. Now, like it's shown here. So, and what happens next? First of all, this electron here will, as we called, thermalize. It will slowly move to the bottom of the conduction band. It will just increase the vibrational modes in the material. So it means it will heat up material for a little bit. And then when it comes here down, it relaxes down in the ground state and emits photon. So all the emitted photons will suddenly have the same wavelength. So we will get the color that corresponds to this particular wavelength. So this is why some of semiconductors, so non-metals, are colored, but some are still transparent. Another properties that I want to mention is light refraction. So when light passes from one medium to another, it refracts. So what does it mean? So it means that it changes the direction, as it's shown here. And the the intensity of this change, it depends on the refraction index, which we annotate as M. So how does it go? Why this is happening? Actually, it is happening because the speed of light in different materials with different refraction indices is different. The speed of light is constant and in vacuum, but it changes in the different media. So when light enters, when a light goes from one material to another, it changes speed, and correspondingly it changes direction in the way that incident angle is not anymore equal to the angle in the new media. So higher the index of the media, lower this angle between the light beam and the normal is. So we can also have a little bit of calculations here. The refraction index, therefore, is a kind of difference between difference is the quotient of speed of light in a vacuum and the speed of light in the medium. So in the vacuum, so speed of light in the media, we know depends on its permittivity and permeability. We can write this as it is shown here. And if we put all that into the equation, we would see that the refraction index depends on permeability and permittivity. I apologize here. The speed of light in the media should have C here instead of 1. This is a mistake. Instead of this number 1, it should be C. So, and then if we enter this expression into the upper formula, we would come out with a relationship where refraction index is equal to the square root of permittivity and permeability. Now, in the majority of non-metals, permeability is about 1, so we can get to an expression that the refraction index is equal to square root of permittivity. Now I would just explain you what this permittivity means. Actually, permittivity is a measure for polarization of material. We will talk in details when we will talk about electrical properties. But just for now, for this understanding, I would briefly say that permittivity is a consequence of polarization in a material, which is caused by some external field. In our case, external electromagnetic field, which basically the light is. Now, at this frequency range, the frequency range of visible light, the only active polarization mechanism is electronic polarization. Electronic polarization means that electromagnetic field polarizes electronic cloud versus electronic atom nucleus. So electronic cloud slightly moves against the atomic nucleus, and that is called electronic polarization. All other polarization mechanisms, which can also be present in the material, are not active due to the very fast frequency of the visible light. Now, about light reflection. You see, nice picture here when this snow cap is reflected in the lake on the surface of the water. Also, the light reflection depends on difference in refractive index of the media. according to this particular equation. So different materials therefore have got different, of course, different kind of reflection, intensity of reflection, and reflection happens in the way that the angle between the light beam and the normal axis are equal on the incident and reflective sides. And yet another thing is the transmission. Of course, what is not absorbed and what is not reflected, it is transmitted. And altogether, as I said, the sum of all three processes is equal to 1, but their share is different along the wavelength scale. So here we see one example of a light interaction with green glass, and you see that it's different, and at different wavelengths, different processes are dominating. So there's almost no reflected light from the glass, just a little bit, but quite a lot of absorbed, especially at the lower and higher wavelengths, but also somewhere in the middle, especially around the green color, the absorption is intensive. This is what actually gives the glass the green color. So in transparent, really, well, not in transparent, in non-metals, we have already talked about this. The color comes from the excitement of the electrons over the band gap, their consequence thermalization, which does not emit anything, it does not radiate, and then relaxation back to the ground state. Therefore, the color is more or less, I can't say monochromatic because of all inhomogeneities in the material, the color have got some kind of different wavelengths, but still the distribution of the wavelengths is pretty much sharp, and therefore we get quite distinct colors out of it. For instance, cadmium sulfide with band gap of 2.4 electron volts would give blue and violet spectrum. Sorry, I have to repeat this. It would absorb in a blue and violet spectrum, but it would re-emit the light in yellow and orange spectrum with the yellow and orange wavelengths. And this is because some of this energy of the absorbed light is lost with this thermalization process. And again, here we have to talk about defects in the systems. For instance, here we can talk about the extrinsic point defects, impurities. And I'll give you an example. Sapphire and ruby, they're both aluminum oxide crystals. Sapphire is colorless, while ruby is dark red, but they have got all the same structure. So why it's so? Very simple. Ruby has got some impurities in its structure. So, and these impurities then absorb light in the frequency, in the wavelength range, where it can emit the red light. And we also can use this doping, deliberately doping, to produce glasses which are stained, which are colored, or even animals or ceramics. So, and then we know what kind of impurities we have to add to the glass to get the color that we want. So if we add copper, we'll get green and blue, or blue. cobalt blue and violet, chromium green, manganese 2+, we will get yellow glass, or manganese 3+, we will get pink glass. So that is the knowledge which it has been developed very long way down in the past. Now, the thing about doping, which I forgot to mention, is that the dopants, they create some states in the band gap, and that allows electrons to move into the band gap, because there suddenly is a new energy level of the dopant. And therefore, from transparent glass, we can obtain some color glass. Now, we talked about sapphire, that is transparent, but you would say corundum, which is also alumina, is not, is white. It's like rarely even translucent. So why so? And the reason is that a single crystal has got no or very, very little defects, line defects, more extensive defects on which the light would scatter. However, the corundum is polycrystalline material and has got grain boundaries in between. And these grain boundaries are defect structure on which the light scatters. And for that reason, the same material in the form of the polycrystalline ceramics is translucent, while the single crystal would transmit all the light. Now, here I said that the light, of course, scatters on the phase boundaries between one and another grain. So that happens also on the phase boundary in very, very different systems. So we were talking in this example, we were talking about grains in ceramics, but it could also be between pores and grains, or in two liquids in emulsion. This is why emulsions, like oil in the water, are white. This is because the scattering of the light. And also that happens between the gas and liquid. And an example is cloud. This is why cloud is white. And it can happen also between the solid particles and liquid in suspensions. So everywhere where we have a lot of phase boundaries, the light will scatter, and for that reason we will see this object white. Now I would like also to go through two applications, optical applications. One is laser. Laser is just the acronym, really. And it says light amplification by stimulated emission of radiation. So here I would like to present you how we stimulate the emission of the light in a laser. Yeah. Now what you see here normally is a slab of single crystal of any kind. This material needs to have band gap, and this band gap determines the wavelength of the light that comes out of the laser. So initially we need to have some excitation energy. So, well, lasers are plugged into electricity, yeah? So, and we excite some initial electrons over the band gap. So when this is done, what follows is relaxation of this excited electron down and emission of the photon. this photon then travels, along the slab of the crystal, and what happens? It spontaneously enable the relaxation of other excited electrons. And this relaxation is not coincidence, but it is in phase and with the same wavelength that initial photon. So what happens is they kind of start traveling in phase coherently together. And more of such event happens, and they come to the end of the slab. Here we have a mirror in order that the photon bounce back, reflect back, and start traveling in another direction. And they trigger more of these events, an avalanche of these events. So finally, we would get an intensive beam of light traveling, or group of photons traveling along this slab. And on the other side, we would have a hole, a transparent hole, through which this light can escape, and actually we would get a beam of the laser light. The laser light, for that reason, is monochromatic, because all these wavelengths correspond to the band gap in the crystal, and due to the nature of the stimulated emission, they would also be in phase. So as you see, for different wavelengths, we are using different materials. We can also have gas lasers, but for the solid state lasers, we are using different single crystals. And of course, if the beam is of different intensity, we can use this beam for all kinds of different processes, from welding, to barcode reading. Some are more, let's say, friendly for a human body than others. Normally, the green light is not as dangerous for our health than some violet light. And yet another application are optical fibers. So today they are so common, but not far away, we were transmitting all the signals through the copper wire. But today we cannot imagine anymore copper wire. The transmission through the copper wire is so much slower than through the optical fiber. So copper wire transmit electrons, yeah? So the optical fiber does not. In the optical fiber, the information is carried by a photon. So you can imagine that this is, first of all, much faster transmission, because this is photon, it's electromagnetic wave. In addition to the speed of transmission, also we can pack much more information into the optical fiber than in the copper wire. And we can send it much further, because we know that the copper is good electrical conductor, but it's not perfect. Still, some resistance exists in the copper wire, and we are losing the signal if we transmit it on the long distances. There's another thing. There's much less error during transmission, because we can produce optical fiber which is much more homogeneous than the copper wire. And in addition, in the copper, electromagnetic field can significantly disturb the signal and the flow of electron. I cannot disturb the flow of photons. So we have no electromagnetic disturbances, and correspondingly, much less possibility for somebody to spy on you. Namely, when electron travels through the wire, it triggers a very, very fine magnetic field, And through this process, we can easily spy on the information carried through the copper wire, while we cannot do that on the optical fiber. So just for you to understand how more efficient are optical fibers. Now, two optical cables that can transmit 24,000 phone calls. Well, two optical cables can transmit 24,000 phone calls at the same time. And if we compare to optical fiber of the 100 grams, this is in terms of efficiency equal to 30 tons of copper with respect to the amount of transmitted information. So we cannot, in today's information era, we cannot imagine that we would have our devices connected with the copper wire anymore, but optical fiber are a solution for that. How do they work? So optical fiber, it's composed of two major parts. One is core, which is inside the fiber, another is cladding. Now, these two has to have different refractive index in order to enable the total reflection of the light on the interface between these two phases. Now, the total reflection of the light occurs when the signal travels from denser medium and cannot cross the phase boundary, cannot refract, but it reflects because the difference in the reflective indexes is so high. So this is actually the mechanism how the signal can travel through the optical fiber without any significant energy losses. Of course, there are always a little bit because we have some defects into the glass where the light scatters. But more perfect glass we produce more efficient and without less losses, this transmission of the information through the optical fiber will be. So this is how the information travels through the optical fibers. Now, before we stop, I would just briefly like to mention yet another different process in the term of in the term of light interaction with matter. Now, when we come down to the nano level and the nanoparticles, well, things change a little bit. Now, suddenly the gold is not yellow anymore. Well, it can be red, or it can even be blue. How that is possible? Well, the mechanisms are a little bit more complex in the terms when we're talking about metals. Now, when we have nanoparticles, colloidal gold, let's say so, this means that we have very small particles, let's say a couple nanometers big, and finely distributed inside some medium. Well, not agglomerated, but they have to be separated and distributed. So we induce color because of the absorption of the light with the surface electrons, which on the surface, the electrons, they behave like kind of plasma. And this plasma can absorb the light and produces so-called localized surface plasma resonance. And you see in this graph, we have absorption of colloidal gold, and the absorption spectra is completely different than the absorption of the gold film. Gold film we know would be yellowish, while such nanoparticles in the form of colloidal suspension would turn out to be red. if the particles would be a little bit bigger, the absorption band will move, and the color will change. Well, also non-metal nanoparticles can suddenly have a color, although in bulk condition they might be transparent. And that happens due to some other quantum mechanism, which is called quantum confinement. We can explain this by again looking at the energy levels of these materials. Now let's go back. Initially yesterday we went through the atoms toward the bulk. Now let's go back now from the bulk towards the atoms. So in the bulk we have continuous bands, continuous valence band and continuous conduction band. But now if you start shrinking down the clusters of material, reducing the numbers of atoms in the materials, you're also reducing a number or reducing the density of the states within particular band. And if the cluster becomes very small, we call it quantum dot, becomes very small, suddenly the levels cannot be considered as continuous anymore, but they are more or less discrete levels within a band. And as a result, also the band gap becomes wider, and suddenly it can give us, after the remission of the excited electrons, it can give us a color. So for instance, one very visually attractive is cadmium sulfate. When we are changing the size of the clusters in colloidal suspension of cadmium sulfate, the suspension will change the color through the entire spectrum. So very small clusters will give bluish color, while then with increasing in size, the color will change towards orange and red. Okay, I think here we came to the end of today's lectures. So now I invite you to ask the questions if there is something which you are particularly interested in, or if something was not clear enough. So I'll wait for you to write down some questions in the chat box.
Thank you, Professor. Yes, participants, please write down your questions in the chat box, or you can raise your hand, unmute you for a while. So we have one question in the chat box. Why light change speed in different mediums?
Yes, light changes speed in different mediums because, you see, in vacuum there's nothing. Light can freely travel. What is light? Light is electromagnetic wave. Now, in a material, we have electrons that are circulating around the nucleus, or we have free electrons, and they all have some kind of charge. They can be also considered as electromagnetic wave, as we know. And suddenly photons can interact with these fields, and that slows them down.
Okay. Yes, any other participants who wants to ask question? Yes, participants, please type your question in the chat box. We'll wait for 2 or 3 more minutes. And if you guys don't have any question, we will probably close the session. Sir, I guess we don't have any other question from the participant.
Okay, so we can
Yes, sir.
close.
Just a second. We have one more question.
Okay, I can read this question. When two atoms bond, the electrons of the same orbits get different energy level. Why? Actually, this we call, well, this is quantum mechanics. We get molecular orbitals, and this is hybridization. We call it like hybridization. Well, I cannot easily explain to you because it's highly quantum mechanic process. But really, it is because two electrons have to be shared now. Now, at atomic levels and atomic energy levels are constrained. We know the shape of these orbitals. If I simplify a little bit, we know the shape of these orbitals. And now, if the electrons should be shared between two atoms, the shape of this orbital have to change in order to encompass both the atoms. So for that reason, we have to form some kind of other orbitals, which we call molecular orbitals. This is, of course, a little bit simplified explanation, but exact explanation can only be given in the term of quantum mechanic approach.
Thank you, sir. We have one more question from the participant. Yes, Mr. Shri, you can ask your question. I have unmuted you. Hello. Sir, his question is in the question and answer section. If you can see.
Yes, yes, sir. Thank you very much for giving me opportunity, sir.
Yes,
Yes.
You can ask your question.
Go ahead. So have we got, okay.
Hello.
Any other
Shri?
question?
Hello, Shri. Can you hear me? You can ask your question.
Hello.
Yes.
Yes, we can hear
Can
you.
I ask question now, sir?
Yes.
Sir,
Please
regarding
go
that
ahead.
optical fiber, I would like to ask whether the specification for this 5G communication and 4G communication, it would be the same.
Sorry, I couldn't understand. Can you repeat, please, slowly?
Okay, just hold on, sir. I'm just doing that one. My question is about this 5G communication optical fiber would be there. I mean to say, is this specification for this 5G communication and this 4G communication for this optical fiber would be the same?
Sorry, but please write it down in the chat.
I guess he's asking, is the fiber communication would be the same for 4G and 5G fibers? I mean, 4G and 5G optical fibers. I guess this is what he's asking.
Is that the question? Now, of course, yes, it is the same. Now, the transmission of the signal through the optical fiber is the same in any technology. It is just then later, how the signal is how the signal is then distributed wireless. If that was the question.
Okay. Thank you, sir.
But
Thank
details I can't tell you because I'm not in the telecommunication business.
Hey, did you get the answer? I mean, I hope you have got the answer.
But you see, we transmit the information, we load on the wave, we modulate the wave, so this is typical in radio waves, or we use digital approach, by sending out the signals that are in the form of binary modes.
Yes, sir. So we have one more question from Ms. Swati Gehlot. She's asking, how does size change affect the optical properties of nanoparticles?
How the size?
How does size change affect the optical properties of nanoparticles?
Yeah, exactly what I was talking with when we are coming down to quantum dots. So it means like maybe several hundred atoms in the cluster. Then we get this so-called quantum confinement, and the bands, valence band as well as conductive band, they're not continuous anymore. Within these bands, the discrete electron levels start to form. And for that reason, the light absorption is not the same as in the case of bulk. The quantum confinement also causes the shift in the band gap energy. So if in a bulk the band gap is below 1.8, let's say 1.7, it easily happens that for the cluster, nanocluster, for the quantum dot, this band gap would be a bit wider, let's say 2.0, and immediately the emitted photons after relaxation of the electrons will be with the wavelength that we see as a visible light.
Okay, thank you, sir. We have one more question in the chat box. You can see when two atoms bond the electrons of same orbits. Okay, he's asking when two atom bonds, the electrons of same orbits get different energy level. Why?
So can you repeat, please?
Yes, sir. Sir, it's in the chat box also. If you want to read, I'll repeat it. Yes, sir. I'll repeat it. He's asking when two atoms bonds, the electrons of same orbits gets different energy level. Why is it so?
Two electrons in the same orbital
Yes, gets different energy level.
get different energy levels. Yeah. Well,
Asking a reason for it.
okay. I'll tell you now. We have, and every energy level can be occupied by two electrons with an opposite spin. So, however, there is still some interaction energy between these two electrons. They don't get paired there on one level, energy level, for free. It still costs some energy. Normally, this energy is lower than energy difference towards the energy level which sits a little bit higher with the energy. And therefore, they both occupied the low energy level. However, in some cases, the next energy level is so close that this price they pay to be coupled is higher than it is the energy, extra energy that the electron needs to sit on the upper level. So in that, we call this high and low spin situation. It happens with some materials like I think iron can be the case, so that we have for the same ion we can have two different electron configuration, and that normally would depend on the coordination of this particular ion. I hope this was the question, and well, this answer can
I hope
be
so.
what you wanted to hear.
Yes, sir. I hope you have given him the answer. We don't have any other questions, sir. But sir, it was really, I mean, great lecture where we get to know about the optical properties. I mean, and some of the facts related to the optical fibers and the fascinating properties of the materials. I hope our participants have gained a lot of knowledge. With this, sir, we'll close this session and we will again meet for the tutorial session in the evening on the characterization of the materials by Dr. Belek. Thank you, sir. We will be closing this session.
Yeah, thank you. Bye bye. See you later.
Thank you. Thank you, sir. Thank you so much.